Remove my glasses. Yes, we came all the way here. So let me take this on the blackboard, just shortly to explain. So briefly explain what we have done and what we're looking for. So generally, there's a bunch of problems in many areas of applied sciences that you come up with models that the mathematical models that are related to the topic of obstacle problem, and we had a few ways of looking at it. One was that we were looking at minimizing the functional. So minimize this. We're always talking about unit world. So everything happens in the unit world. It can be very general, but we skip the generalities here. So we are minimizing the functional. So this is a functional. We're minimizing it over set k, and k is the function w12 g intersected with the set of functions that are larger than psi. What does this mean? It means, this already is clear that psi is given. So we had also g psi here maybe. So psi given function. So this is a given function. G is a given function. So this is boundary data, and psi is the obstacle. So this is psi, and your boundary data, G. So you can think in the higher dimension. And then you're looking for functions V here. This is the function V. It has to always stay above psi. Of course, it can touch also. Something like this can happen. And then you're looking for the space W12G. So this G relates to the boundary data. So functions are boundary data G. W12 means that that the function V and its gradient are in L2. Okay? So we are in L2 space. It goes for the function V and its gradient. And we're trying to minimize this functional. This is the name for this is Dirichlet energy, or Dirichlet integral. So Dirichlet energy is minimized. And when minimizing this, you realize that if this doesn't touch the obstacle, then what you can do is make variations. So I think I'm going to say a little bit about variations, but I think we can do that as part of the exercise part. So you can make a variation here on both sides, up and down. So it means that you can change your function a little bit and put the new function here, see what happens. And you do that with slight changes, very slight changes. And then you will go back to the minimizer and see, you can compute that, and we will do that, and we will see what happens. But if you're here, then you can only make a variation upwards, but not downwards, because if you do downwards, you're contradicting this. You're violating that condition. So it means that at sets, when you're touching, you cannot make variation downwards. You have to only do upwards. When I'm saying upwards, then I mean if V0 is a minimizer, let's say this is a minimum, we have phi, then you do plus epsilon plus some function, let's call it phi. It's a smooth function. And phi is non-negative, epsilon is non-negative, then you go upwards. Okay, you take always phi to be non-negative for simplicity, and then epsilon can also change sign. Then it means that you're making phi negative as well. But you see that here you can do that, because it's okay to go downwards, you still are above this, but here you cannot do that. So that gives you a very special PD generally. So on this side it will give you sort of a function that is varied on both sides, and we will see that variation on both sides give you an equation which in this case will be a harmonic function. So it gives you the harmonic function here, but on this side it will not be the harmonic function, because when you're touching the function is actually psi, you cannot do much about it. When it's not touching here, things may happen. So these are a very specific point. These are the three boundary points. And the question is exactly, so the whole program is about this point, what happens here. Because this is far away from standard partial differential equations. So what we did, we looked at this and then we realized that we can reformulate it. I think you had some exercise for yesterday to do. So we reformulated. And we called the function u to be v minus psi. So we subtract the obstacle. And you're supposed to compute this. So I can just do it for you. And what we have is, this is Laplacian of v minus Laplacian of psi. And if we can verify that v is harmonic away from the obstacle, so it means that Laplacian of v, so I have to verify this, that away from this is going to be 0. Laplacian is going to be 0 because it's harmonic, but when it touches it will be Laplacian of v psi, so it will be Laplacian of v, it's going to be Laplacian of psi, and characteristic function of when v is exactly psi. And then you have minus Laplacian of psi. And then you just, and of course something else, because we really don't know, plus something here. Because we don't know what happens exactly at the free boundary. Because when you're touching the function, let's say in the interior of that domain, in the interior, Laplacian of v equals exactly Laplacian of psi. But on the boundary, you don't know that. Think of this, just for simplicity, think of this function. Think of the function which looks like this. 0, and then, so this is the function x plus. So Laplacian of this function is 0 on this side, it's 0 on this side, but on here exactly is going to be a measure, is the Dirac mass. And this is also something like that. So we call it, yesterday we called it a measure mu, which lives on the boundary. We don't know what it is. I would prefer it to be 0. Because if it's 0, I have a stronger base to work on. And we will show today that that's actually going to be 0. Okay? So what happens here is that you get, if you just subtract this and this, you're going to get minus Laplacian of psi, which is this one. It takes out this part, but not completely. It's get v is larger than psi plus the measure. And then we call this function for f, just gave it a name, f, and then this is exactly u is positive. The v minus v is larger than psi means that u is positive. And then the measure is here, so you get this characteristic. U is positive plus the measure. So you start from your backboard there, a green board there, and then you have your function model v, minimizes this. You come down by reformulating, you get this. The only thing you need here is that this function f, which is the Laplacian of psi, belongs to, in order to make a definition for this, because you're taking second derivatives. So you can allow it to be C2, but you don't really need that. You can allow it to be W2 function. So you allow that the second derivatives of psi be in L2. Then this has a meaning, weak meaning. So in the weak sense. So all you need is that this function is in L2. F is in L2, it means that psi is in W2 too. So W22 would mean, if you go back here, W22 would mean this, and the second derivatives are in L2. Then it has a meaning. So you see that the assumptions are very, very little here. Okay? And we are aiming at proving that this measure is 0. Or this measure here is 0. Because if that's 0, then you see that the problem becomes a little bit simpler. It's a very nice problem. Well, here already you don't know what the measure is. So that's already a, that's already a problem. So you have to get rid of it. Preferably. Not in many, in this problem you get rid of it. But there are free boundaries you don't get rid of it. That's actually, all information is there. The problems like Bernoulli problems, free boundaries that I told you about yesterday at the beginning, there are other free boundaries that this measure actually contains a lot of information. You don't get rid of that. That's the measure that gives you information. Okay, so let's go on. See. So let me clean the board so I can get, no, not this one, I guess. Yeah. Okay, so we're trying to, I just gave you a minute to look at this. We're trying to get rid of the measure. So the first thing is, I want to prove it's non-negative. So I will prove this measure is non-negative. Then I will prove it's actually going to be 0. So I need the non-negativity of that. So we're going to use a lot of, you will see that already proving this needs a lot of tools from analysis. Okay. So let's start looking at this function. So eta is a very smooth function. So on the unit wall, the function is very smooth. It's not negative, and it goes to 0 very fast. So it's infinite times differentiable. And then you take eta times characteristic function of a chi epsilon is not the characteristic function, but it looks like that almost. So you sort of, you look at, so let me give you a picture here. So you look at the level sets of U at 2 epsilon level. Okay. And then you look at the set when the function is 0. And in between, you have different values. Okay, so in between, I forgot to have the epsilon. And here's the. Am I correct? This is. Okay. So this is the set U is larger than epsilon. This is the set U is epsilon, exactly. And what you do, you define your function phi epsilon to be 1 here. So chi epsilon is 1 here. Chi epsilon is 0 here. So you have the freedom of defining a function. And your freedom is like, in this set, when u is larger than 2 epsilon, you define it as 1. U is less than epsilon, you define the function 0. And then in between, you define it like this. And you see that when u is epsilon, this is going to be 0. So your function chi epsilon is going to be 0 here. And then it grows with the value of the function u itself, in that way, until you hit the value 2 epsilon. At 2 epsilon, it becomes 2 minus 1, that's 1. So you go over to 1. So the function is 0, and then here it changes, and then becomes 1. This is a sort of cutoff function. So we use a cutoff, and the cutoff is using the function u itself. That's the best way you can do it through the level sets. This is meaningful because our function u is continuous. We haven't, though, shown that the function is continuous. Remember that. And I was not planning to do that because that already will take a few hours if I want to go through it slowly. So this function u is continuous, so let us assume that. We can give you references to look at that. Actually, usually proving continuity is harder because that's the first stage. You have to use Harnack inequality and all that and geometric properties, so that's usually harder. But there is just one technique, basically. Always you do the same. So you don't need to be inventional. You just do whatever people have done classically. So it goes always through. But you have to go through the machinery, which we skip here. So we assume it's continuous. I was actually trying to prove this in a different way, and it seems that it can work, but it is much simpler. But I was worried about one point, so I didn't want to take it up here. There is one point that I was not sure about. So anyway, but we do have continuity when it's strictly positive, and that's much simpler because we have harmonicity. So it's continuous when you're strictly positive because it's harmonic. Harmonic functions are analytic functions, smooth functions. But the problem is when you approach the boundary 0, you don't know you really hit 0 or not. You might the function come to 0 from all directions. Maybe one direction you jump to 1. You don't know that at this stage. Okay. So this is our function, and we'll see how we're going to use that. Now we're going to use a lot of classical analysis. So we take omega plus, which is the set when you're strictly positive, and you're assuming continuity. So well-defined. So this is an open set. So this is a place I need continuity. That omega plus is an open set. Okay? There's an open set, and then I will take gradient of u times gradient of eta epsilon, and I will get this back. I will leave to you to verify it, so please write down to verify this. So the verification of that has to do with that actually Laplacian of u equals f in the set u is strictly positive. That's the reason. And in the weak sense. So in the weak sense, it means that whenever you're applying a function phi and integrating like this, and that would be my phi, you're going to get back phi times f, basically. And now I'm choosing a very specific phi, which is related to the function u. And then I can do the analysis. Okay? So if this is so, in the set u is positive, it means that what you're going to get is on one side, Laplacian, so let me do it like this. So Laplacian of u in order to write exactly in that way, I will do it like this. And then if they are equal, then this are going to be equal for any function, smooth function. For any smooth function, they are equal. So the smooth function and compact support, with compact support, then you just integrate and take integration by parts, and then you go on the boundary value will be 0 because of this guy, phi, and then you get gradient of u, gradient of phi, and with a minus sign here, and then here f and phi survive. And then you're doing everything in omega plus, and I'm letting f phi to have compact support in omega plus, then this is pretty much what I'm going to get. But now I can choose any phi which has compact support in omega plus. I'm choosing the phi I just created. And that phi is related to the function u. Okay? You can choose whatever you want to, but only thing you need is that phi has compact support in omega plus. And the function I gave you, that has that property. It's very cold here. Yeah, it's extremely cold. And I was worried about getting heated here. Yeah, because this is it's blowing extremely cold. I don't think you feel that there, no?
No, not here, but if you sit here, yes.
Yeah, okay, yeah, special. You can slow it down a little bit. Okay, so let me see what happens. I can wait. So let me go to the end of it and then go back because it's easier. So this looks like pretty much what we had, yeah? If we go, no. If we go back here. Oh, I didn't even continue here, I'm sorry. Yeah, I have to continue here. Okay. So we start with this. That is just the definition and nothing else. That Laplacian of u is f inside omega plus. And then what I do, I take the gradient and apply it on eta. So the gradient applied on eta epsilon, you have to separate. Eta epsilon was written in a very specific way. And let me write it down here because we want to relate to that. So here it is. So what you have is eta epsilon is eta characteristic function epsilon, and this function is like 1 u over epsilon minus 1 and 0. Now when you apply gradient to eta epsilon, that's the product rule. So gradient applied to eta epsilon, that's the product rule, and this is what you get. So please try to verify this for yourself. So you apply it first to the eta, and then you apply it to she epsilon. So eta survives, she epsilon, if you apply it, it will be 0, 0, and then the gradient of u. So that's the reason you have gradient of u power 2 here. It's a simple computation, but please write it down.
I have a kind of stupid question. Here, of course, when we draw it like this, u equal to epsilon and u greater than to epsilon, we draw it as a curve, but it can be a set, right?
What do you mean it can be a set?
Like it may not be a nice.
It is not nice. It is not nice.
It will be, but to draw it is very nice.
Yeah, that's. This can be very nasty.
Bad, right?
This can be very nasty.
Because we at present
Disconnected.
we
don't have no information. I'm just giving you the best scenario.
Right?
Yeah, I'm giving you the best scenario. Yeah, it can be extremely nasty. You can come up with anything. I mean, yeah. This is, of course, this is not.
It is like a big open set.
Oh, it can be very nasty. But it doesn't really matter. I don't care about that because computations don't see that. We are not looking for how it looks like. but we're looking at taking the gradient. This is the answers we're going to get. This is formal, exact. This one is not even close to the truth. But that's the picture we can give. I cannot give you complicated pictures. Yeah. Okay, so this is what we get when we apply the gradient applied to eta epsilon. This is what we get. And of course, this guy here is non-negative. So I get this is larger than or equal to just this part. Can just slow it down a little. Okay. So what we have next is that the product here is bounded also. Let me see why you can see that. I have to take a distance. Okay. So I need this to be bounded. Yeah, because eta epsilon is bounded by eta, so I can actually let me go back and tell you why. I don't get it myself. Let me see. Why do I have that this is bounded?
U is in W1.
Sorry, what?
U is in W1.
Is in W12, yes. So the gradient is bounded by Holder, applying Holder, and yeah, that's it. Yeah. Yeah, thanks. So apply Holder, then we get the whole integral is bounded by the L2 norm of the gradient U and the L2 norm gradient of eta. And eta is very smooth, so that's bounded. Yeah, okay, I'm sorry, yeah, I didn't read and. So this is obvious, yeah. I thought it was following from this, I couldn't see that. But so since we have this one and this one, okay, this is obvious because psi is always less than 1. So this is less than eta. And this integral, apply Holder inequality and use that gradient of u is in L2, and eta is very smooth, so this is bounded. This together with this allows us to let epsilon go to 0 and use the dominated convergence theorem or bounded Lebesgue theorem. And then you get that the integral will actually converge. So you let epsilon go to 0, and the integrals, we have an integral here with the epsilon, but that will converge to gradient of eta. You're going to get this one, and then this guy also eta epsilon converges to eta, and we're going to get this one. So on both sides we get convergence because of classical dominated convergence theorems. And this is what you're going to get. You're going to get this inequality. And we have also used that the gradient of u is 0 almost everywhere in the set omega plus complement. Okay? Because u is 0 there, so it means gradient of u has to be 0 almost everywhere. Not everywhere, but almost everywhere. Okay? I would challenge you to verify this. It's a advanced calculus level. So try to verify why is gradient of u 0 almost everywhere. You have to probably go back to your measure course, Lucine's theorem, what we call it. Okay. So this is what I'm saying, we have used this. So the last inequality tells us what? It tells us that the measure I have actually is non-negative. Okay, so again, I suggest that you will check this. Why is this suggesting that the measure is not negative? It's a good exercise. Well, you have to go back to your equation. I don't have it here anymore. So go back to the equation for u with the measure. Okay, write it exactly in these terms. You have an equality with the measure when you're writing it. And then it says that this is less than this. It means that that measure has to be non-negative. So it's a good exercise. You can do that in the afternoon or maybe all those exercises.
Maybe tomorrow.
For tomorrow, okay. So put down so we can always, we can go back to the slide and do the exercises. These are advanced, I would say, undergraduate level. So it's a good exercise. Many times in the books and the PDE books, you sort of pass through this, but you don't really put attention to these things. Very, very important, small technical details. That if you know the topic, then you know it by heart. But as a student, you always have to do it until you know it by heart. Then you don't do it anymore. Here already you get 3 questions, I guess. So let me go on. So the question was, why does it mean that gradient is almost over 0? Why do we have equivalence here with the fact that mu is non-negative because of this PDE? So we arrive here, but don't forget that we have another PDE when the measure is involved, which is equality. Okay? Then the answer is there, basically. So it tells us that Laplacian of u equals to this, and that measure is non-negative. So we are halfway. Now I'm going to prove that that measure is also less than or equal to 0. I get rid of that. Well, I will not prove it is less than or equal to 0. I will prove that that measure is actually going to be a kind of bounded function. I'm going to prove that it's kind of bounded function. Is larger than or equal to 0, I will prove it's less than or equal to, not 0, but less than or equal to a function somehow. And that function is in L1. And the measure is living on a set and it's bounded by an L1 function, and that will trouble us, and that will give us the possibility of deducing that that measure has to be 0. It will be in the next page. So let's see how it works. Okay, I told you about variations upwards. So you can make a variation upwards. Always the picture is you have the obstacle, and you have the possibility of making your minimizer a little bit larger by adding a function to it. So this will not be a minimizer, but the integral, the Dirichlet energy will be larger. You're changing your minimizer, you look at the energy of that has to be larger than or equal to. So take any function like this, and you know that this is going to be larger than or equal to 0. Okay? So again, verification point for you. Did you, by the way, send out the... No?
I did split.
Okay, this probably you should
I
do
will do it today.
today.
But this is also included in
Everything
it's
is...
a whole lecture, only one PDF.
The one I sent you, did I send you yesterday again? Okay, I will send it to you, so we
So
just...
it is a complete lecture.
Yes, this is the complete lectures.
Yesterday's and today's.
So everything is there, one lecture.
So then I will like.
It's called 1 by 1.
Yeah, so I
I think I sent it yesterday, but I will send it.
will check.
Okay. It's much easier for participants to look at it. Okay. So from here, you actually get the Laplacian of u is less than f times characteristic function omega plus closure. And of course, we're using this. So what does it tell us? It tells us that at one side, Laplacian of u equals to this. That was previous page. And now we're getting that this is bounded again by this function, f times characteristic omega plus. Pay attention to omega plus and omega plus bar. And the function f is bounded. F is bounded. Even if it's L2, that would be nice. Still can work for us. So this guy, what does it tell us? If you write f of a characteristic function over omega plus bar, you can write it with this one and then on the boundary part. So this part will disappear with this one. What remains is the boundary part. Only on the boundary part. And it will tell you that the measure is larger than or equal to 0 and less than or equal to this one. So what we have is that Laplacian of u equals to h. Okay? So Laplace, this guy here, I call it h. And h is between these two guys. Okay? So h is going to be between these two. And they're both bounded. Okay? Pay attention to this. Laplacian of u is h, and h is between these two functions. Here u is strictly positive, is exactly omega plus. I'm just rewriting. I don't know why I'm rewriting it, but it's omega plus. I could have used the same notation. So what we have is Laplacian of u is h, u is larger than or equal to 0, h is between these two guys, and f is a smooth function, or bounded function is enough for us, basically. And h is bounded by c. Because this is bounded, and this is bounded. Okay, so if Laplacian of u is a bounded function, you already told us yesterday that we're going to get this W2P function, C1 alpha function. So you realize that now, without looking at this, you realize that if your function is 0, and then it goes off being positive, so I'm talking about the function u, it's 0, it goes off being positive, it can never be something like this that my picture was, because it's C1 alpha. So C1 alpha means it has a gradient. And if the function is completely 0 here, the gradient has to be 0 there. So it means that the gradient is also exists. So it's a very smooth function. And that forces already that this measure that you, in that example, was a Dirac mass. That measure is not there. So the function x plus was not an answer to our problem here. So it looks like the function x plus to power 1 plus alpha or something like that. And if you take the Laplacian of that, then you're not going to get a Dirac mass. X plus you get a Dirac mass, but x plus to power larger than 1, you don't get Dirac mass. So what happens here, again, one exercise for you. So this part is also an exercise for you, the last sentence. So what you get is that d2u is actually 0, almost everywhere in d1 minus omega plus, because u is 0 there. Again, the same conclusion. If u is 0, all its derivatives are going to be 0 almost everywhere. So what we're going to get is that the measure is 0 almost everywhere. Okay, so the measure is 0 almost everywhere, but mu is also bounded. So think of a measure which is 0. Think in terms of measure theory. A measure which is 0 almost everywhere. And it's also bounded. So measure is represented by something times characteristic function. And it's also that something is bounded. So the measure is like, let's say, k of x times a characteristic function. But that characteristic function is 0 almost everywhere, and that function k of x is bounded. What can you come up with? Think in measure theory. So this is another exercise for you, which is the last line. So if your if your measure mu is k of x, characteristic function of a set, let's say D, and D has volume 0, if the volume of D is 0,
so D has Lebesgue measure 0.
yeah, the volume or the Lebesgue measure, yeah. So Lebesgue measure is 0. And K is bounded. What are the possibilities for the measure mu? What is mu? Well, the only chances is that mu is 0.
Plus it's non-negative.
I know.
We will use.
Does it matter if it's not negative?
No,
It doesn't really matter. K is bounded. Yeah. I think we used non-negativity at some point here. I don't remember it right now. So that tells us that that measure has to be 0. Because if the measure has a support, if the measure has a support which is very small, then, oh, thank you. If the measure has a support which is very small, in the sense of Lebesgue, measure 0, then that measure has to be like a surface measure, has to be like a sorry, I'm getting or Dirac source, things like that. So pure point measure or continuously singular measure. But that means that that possibility is gone. So you cannot have that K has to be sort of unbounded. So you don't get it. Okay? It's a good exercise for advanced undergraduate students. So conclusion, that the measure is 0. And it has to be the characteristic function times the function f. So voila, I would say that we really got this all over, not only in the positive set, but all over the ball of radius 1. So we got that this is larger than or equal to this. This is Laplacian of use f when in the whole ball v1. So we have what we were saying yesterday, that we can go from minimizing the Dirichlet energy gradient to power 2 over v is larger than psi to looking at the PD Laplacian of u equals to this, with h being this guy. They are the same problem, and now we have proven that. So you realize that this information here, this PD here, with h being like this, so let me point out here, that information is much better information, because I don't have this extra v is larger than psi. Everything is in one PD. Okay, everything is in one PD, and it looks like very much classical PD. There's little bit differences, and that difference still makes a lot of trouble. But still, we have Laplacian of u equals to f times characteristic function of u is positive. And let's not forget that from here, we also have directly that we have a C1 alpha or W2P solution for any p less than infinity and any alpha less than 1. If you're not familiar with this notation, C1 alpha means that the gradient of the function is Holder alpha. I'm aiming at proving that alpha is 1. Classical PD will not be able to give it to me. So there's no technique in classical PD. You saw yesterday with this computation we tried to do, with taking the derivative of the potentials, that would not go all the way through unless f is very smooth. In our case, it's not only one f, it is f times this guy. And that's not smooth. This guy is smooth, but not this one. It is just a bounded function. Okay, so let's go to a little bit of classical PD just to see what is what. So if the right hand side is C alpha, the solutions are C2 alpha. You can actually bring it down to Dini that I suggested yesterday. You can bring it down to Dini. So if the right-hand side is Dini continues, then you get C2 with no alpha anymore. It's C2 and you get I don't think you get the Dini continuity back. I think you get half of that or something. And I'm not sure, but I don't remember it. But I think it don't. Anyway, so Dini gives you C2, C alpha gives you C2 alpha. And you also realize that if you even have continuity, which I'm not writing here, so even we had an example that even the right-hand side is continuous, the solution doesn't necessarily need to be C2. There were specific examples and you were supposed to compute that. Did you compute it?
We'll do it today. We'll make them do it today.
Okay. So you'll have some exercise sessions and training sessions. So the right-hand side is bounded, so we go down in irregularity. You go down in irregularity, you go down in irregularity on the other side. So if it's bounded function, the right-hand side, so when I'm saying right-hand side, I'm talking about f on the other side, basically. It's not a free boundary anymore. It's Laplacian of u is just f. Forget about free boundary right now. Then you get C1 alpha. I will also challenge you to do the computation as I suggested with potentials. Because you can always do that by looking at the potential. Do they have your lectures? No. Your notes? Maybe you can also send it. Yeah, so if you look at we call it UF, is F. I'm doing in dimension larger than equal to 3. Dimension 2, you have to replace it with logarithm, and then integral dy. If you look at this function, let's take it over b1, doesn't really matter. The Laplacian of uf is going to be, in b1, is going to be f, basically. Well, let's put a constant here so that we make it f in b1. I ignore anything outside b1. Otherwise, it's going to be a little bit more complicated. And then Laplacian of u here is also, or in that example, is f. So it means u minus uf is it. So this difference is harmonic function. And the harmonic function, yesterday we saw they're going to be C2, at least. They're analytic, but C2 is what we're looking for. So this function is C2, and I know that the potential written like this is also C2. C1 alpha, we're talking about C1 alpha. We're talking about the right-hand side being L infinite. So this is analytic, it's C2. This guy is C1 alpha, so it means that U minus, so this is C2 and this is C1 alpha. It pushes that this guy to be C1 alpha as well. It cannot be worse. Okay, but it's going to be C1 alpha. So you get C1 alpha. So I'm asking you what to put here. I don't know. What to put here to get C1, 1. I want to push alpha to be 1. So what am I to put on this side to make it? So just to look at a very simple example. See, if you take the function x, take plus side to power 2. The Laplacian of this function is, what's the Laplacian of this function? It's 2 times characteristic function over x is positive, yeah? So it's 0 and 2. And then it jumps, Laplacian jumps. So this function is our f, and this function is our u. Now f is what? F is bounded, L infinity. Okay? So f is L infinity, and f is what? U is what? We know it's C1 alpha from that answer, but if you look at the specific function here, what can you say? Well, it's one-dimensional, so it's really second derivatives. I'm saying second derivatives are bounded. So the function is C11. That is the first derivatives for Lipschitz. So I'm actually, even with something like this, I'm getting better than this one. But there's a structure here. So that is not wrong. So this guy is not wrong, but this guy doesn't give you all information. If there's a structure, and the structure here is what? If this is the function u, so what I'm saying here is when u is positive. So when you have a certain structure like this, like free boundary structure, so this is a free boundary type of structure, then actually you get a little bit more. Tiny, but a little bit more. So if there is so here the answer is, well, in general, there is no real answer to this. But I would say that if this right-hand side is coming from a free boundary of obstacle type, then you really are going to get C11. Of course, if you put a very smooth function, you would get more, but I'm saying not more. I want to stop at C11, but no more regularity. If I would put F is, the right-hand side is C alpha, then of course I'm going to get C11 also. But I don't like that. I don't want to get a continuous second derivatives. I want to stop at C11. What are those examples? And those examples are exactly the borderline when free boundary is coming in. So free boundaries, and this is not one example, C11. There are examples with Lipschitz, and you don't get C1. Those are Bernoulli type free boundary. You can actually make it C21, but not C3. There are a bunch of examples you can do that. Okay? So free boundaries usually give you a borderline, and that's it, then you stop it. The next level would be a different problem. And that makes it different from the classical.
It is optimal kind of.
It's always there, yeah, always gives you the optimal one. Exactly. If you would look at the so-called thin obstacle problem, then you have also like 1/2, 3/2. You get those halves also. But these are also the borderlines. So very nicely they come up with this all the, but you don't get better than that. Okay, so the free boundary, as I suggested, it's not only, so if f is just smooth function, so I'm saying f is a smooth function, I have to assume f is C alpha, but still I have a characteristic function, so it doesn't fall in this category, because this f times this is not C alpha, it is only bounded function. So I'm putting an f which is smooth, but f times this is not smooth, so I will fall in this class. Because I have a structure. That structure is very important. So what you're going to do is try to show this, try to prove this. And why do we get that? Well, prove this one. Or C11 locally. The word local here, LOC, is mean that I don't want to, so I have a boundary, fixed boundary, like the boundary of the ball. I'm working in the ball of radius 1. I don't want to go close to the boundary because there are surprises by the boundary value G. I don't want to involve that. So I'm always working in a half ball. I'm not affected with the boundary values. So if you solve a PDE in a ball of radius 1, or in any domain omega for that matter, if you stay away at fixed distance from the boundary data is not really affecting you in the terms of regularity. It will never affect you. It will affect you in terms of the norms, but not the qualitative theory. Okay? Amounts like how much is the second derivatives, the norm of second derivatives, of course, is affected by boundary values, but not whether it is regular or not. So in free boundary problems, most of the cases, I would say 90-something% of the cases, you don't look at boundary values. Unless you want to prove existence theory, then you're done. You go always in half ball or something. Whatever you do it in a ball of radius 1, and qualitative theory in half ball. What do I want to prove now? Okay, some assumptions. So from now on, I'm going to look at the function f, the right-hand side, which is strictly positive. I will actually assume it is 1. The reason for this is the following. You remember what f is. F is minus Laplacian of psi. So if you remember what f is, okay, in our problem, so I'm looking at my problem at the beginning. So f is like this, and then you have, this is psi. And you're minimizing your functional. And the minimizer, this guy v here, we also saw Laplacian of v is less than or equal to 0. It's a super solution. If it's a super solution, think one-dimensional. It's always going to be concave. So if v is concave, it means that v might be something like this. Oh, this is not good. Let me make a picture. You see, I'm assuming that this is positive. It means that second derivative of psi one-dimensional is negative. Second derivative is negative. It means I'm looking at these points, basically. Here, second derivatives are positive. I'm not interested in that. And the reason is that my function v will never see them. It costs too much to go down and see them. So I will not go down and see them. Okay? So I'm touching only on the concave parts in dimension 1, only on concave parts of psi. In higher dimension, also I'm touching only on the concave parts of the concave in the sense of Laplacian. So minus Laplacian of psi has to be positive. So I'm touching those. I cannot touch when it goes. If I touch it, it means that I have a very specific psi, and then, well, of course I can touch it, but still it has to do with what the energy will be. And those points are not so good points for me. For regularity points, they are not good. You can actually create free boundaries which have volumes, positive volume. You can see that in a paper by myself and Björn Gustafsson. I think you know the place probably where you can suggest that. So there is an example with F changing sign, and you get the volume of the free boundary as a positive volume. That's a simple example, 2 lines example. But you can actually create that. So we're assuming F is positive. From now on, F is positive. And I will actually soon set this to be 1, because that's it. I mean, 1 or positive is the same thing. If you're C alpha, that's it. You will also see the reason that why this is not so much restriction. And that has to do with scaling techniques. Okay. So I will assume F is identically 1. That simplifies everything for us. So, what?
Can we take a break? Or
Yes, we can take a break.
because maybe before you start.
Oh, okay. So let's take a break.
Do you want to take 1.5 hours in the first lecture?
It doesn't matter.
No, I have to ask you. So according to you can.
For me, it doesn't matter. What do you mean with the?
No, means I have arranged your talk like 9:30 to 10:30.
Okay, then we do it. Let's arrange it. Yeah. Okay. When I'm going, I'm just going.
Yeah, but that's fine. It takes a
It's like
because for us also to that thought process is continuous. So
Yeah.
it's
so that probably is a good place to stop
Yeah.
because we will talk about different techniques. I know this also in my classes, and I all of a sudden it's just 10 over. Students are. I'm not that much sensitive to students taking break.
yeah, I was not sure. Otherwise, I would have made like we have 2 hours.
No, this is actually a good place to stop. Now it gives you a break to work even more. But because we start on a new thing, so it's good.